Morning, guys. So yesterday we introduced the whole notion of a reaction mechanism. Basically, we may have a net reaction and overall mechanism that goes from reactants to products. What a mechanism specifies is the actual sequence of steps. Sometimes it's a 3-step pathway, sometimes it's a 5-step pathway. Each step is referred to as an elementary process. Each step is a reaction in itself, so it has an activation energy barrier. Usually the one that has the highest barrier is the slowest step. They would have to tell you which one is the slowest step, and we give that one a special name called the rate determining step. So I'm going to give you one quick example with that. We're going to have another look at our elephant toothpaste demo, and then today we're going to finish off with our Arrhenius section. We've been studying rate orders for a little while now. We actually want to just come back and actually figure out what does the rate constant depend on. We've been saying, yeah, it's temperature, but how? We're going to see how we can actually do an experiment to actually calculate what the rate constant actually is. All right. So I'm going to start off here just as a warm up here, just a nice quick practice. First one, they're going to propose a mechanism to you. I'm going to give you that the net reaction, the overall mechanism is 2NO runs into an O2. This becomes 2NO2. I'm going to give you this is actually a 3-step process. So we have step 1. Step 1, again, you're not going to be asked to propose this from scratch. But you're going to be given most of it. I'm going to leave out step 2. I'm going to ask you what step 2 is. Step 3 actually involves N2O4 becoming 2NO2, like that. All right. So in this question here, I want you to just analyze for me, see if you can determine step 2, and then also see if you can identify any intermediates. So just make a list. Remind you here, an intermediate is something that is formed early on. It's made in some early step, but it is consumed later. So it appears as a product in one step first, and then it's consumed later. Right? So let's just try that out here. This time they've given me the net reaction. This is the sort of, here's my project, build this house. Right? I usually just do it by a puzzle here. So I usually say, okay, so in total I have 2 NOs. Well, I see the 2 NOs going into first step. That's perfect. I see an oxygen here as a reactant, but I don't see it in step 1, 2, or 3. So maybe oxygen has to be, I'll use a different color here, put oxygen here in step 2. Because that way both of these are reactants, both of these can actually be on the left-hand side. Now what about the right-hand side? Great. I produce the 2NO2, I see that at the end of step 3. Notice sometimes products can be made in an early step as well. As long as it doesn't cancel out, it's still a product in the overall. However, I see some intermediates. I actually produce N2O2. I don't see N2O2 overall. I don't see N2O2 being cancelled out in step number 3. That must mean N2O2 actually gets cancelled out in step number 2. That one there is an intermediate. That cancels out, and therefore it doesn't appear in the overall. And suddenly step number 3 has this weird N2O4 chemical show up. So maybe I need to have an N2O4 here. This is what I mean by a puzzle here. I just want to make sure I cancel out everything else so that I'm left with 2 NOs and oxygen becomes 2NO2 here. Right? So in that, I've been able to calculate step number 2. Basically, I'm adding these steps together here. I'm identifying intermediates here. Both the N2O2 is created in an early step, used up later. Create N2O4, used up later. Both of these ones here are referred to as intermediates. I'm just going to show you another strategy you can use to actually solve this out here. Essentially, what I've been saying is the net reaction is actually the summation between reaction 1, step number 2, and step number 3. You can actually do this by algebra. You can rearrange it for step number 2. If you wanted to find step number 2, imagine taking your net reaction, minusing step 1 and minusing step 3. I can take my net reaction minus 1 and minus 3. That's just what algebra says, right? So let's just try it out here. The net reaction, I'm just going to copy out 2NO and O2 becomes 2NO2. When I want to minus reaction, a minus means a flip of the equation here. I'm actually thinking plus the opposite of reaction number 1, plus and minus 1. So reaction number 1 had 2 NOs becoming N2O2. The flip of it would actually take N2O2 becomes 2NO. That one there is the opposite of reaction number 1. And let's also add it to the opposite. So I'm thinking of it as a plus, the opposite of reaction number 3. Opposite of reaction number 3 would have 2NO2. I'm switching products and reactants. This ends up giving you N2O4. Right? So let's cancel out things. Don't try to identify intermediates from this point, because I've just totally played around. I've mixed things up. This is actually going backwards and whatever. This is just a mathematical trick. If you're having trouble finding what step 2, you can find it in this fashion here. So in this case here, for example, 2NO2 cancels 2NO2. The 2NO cancels the 2NO there. And there we go. We have N2O2 runs into O2, gives you N2O4. And therefore, I've reclaimed what step number 2 is. All right? So just another way of doing it here. They're always going to give you basically all the steps, and there's always just going to be one missing step. Usually they give you all 3 steps there. They would need to tell you which one's the slow step. So if, for argument's sake here, I told you step number 3 is slow, I wouldn't be able to predict that. But if they told you that step number 3 is slow, you can call this one here the rate determining step. Our overall speed of the process depends on the slow step here. Our rate determining step. This is the one that's the slowest. So this is the one with the highest energy barrier, the highest EA. And therefore, if I tried to find the rate law, I would have the rate law, even though realistically it has NO and O2 and things like that, because it really only depends on the N2O4. I want to say something like rate is proportional to N2O4. Obviously, N2O4 here is an intermediate, so we actually need to backtrack and we need to say, well, the N2O4 would have been made by O2 colliding with N2O2. So this becomes O2 and N2O2. And then we also see another problem here. Could have chosen an easier one. N2O2 is actually intermediate, actually made from 2 NOs. I can think of this one here as an NO squared. Right? So if I actually know the mechanism, if I actually know which particles are actually doing the colliding, I can actually use that to my advantage to actually determine the rate law, to figure out the orders. Otherwise, we can't just look at the stoichiometry. We can't just say, oh, NO squared, oxygen here to the power 1. I can't just do that process there. All right? I'm going to do a quick little detour here. So far, we've just been analyzing an intermediate. I want to just give you another example of a catalyst here. I'll walk you through this process here. We'll see if we can do a little bit more practice with rate determining step, and then we'll switch over to our Arrhenius equation. I'm just going to pull it over to the right here. Maybe just do this on line paper. Just as a new question here, I want us to revisit the elephant toothpaste demo. So if you remember, for elephant toothpaste, the reaction was quite simple. The reaction was taking 2 hydrogen peroxide. It reacts. This is a very slow process, a decomposition into water and oxygen. This is our balanced formula equation. This is not where we're going to get our rate law from. So this is the one that I had the long clear gas grad cylinder here. We had the H2O2, and basically it was just sitting there. Right? It didn't look like it was doing much. Basically what's happening here is, as proposed here as a net reaction, the 2H2O2 here, the energy requirement is way too high. This reaction here is a very, very slow step. What you saw for our demo, obviously we added in some soap so it can actually trap some of the oxygen bubbles. We added some food coloring. By adding a catalyst, I threw in a catalyst here, Ki. It's actually the iodide part of it that actually catalyzes this reaction. So it's actually just the iodide that I needed. What I'm going to do is I'm going to get us from the same start, the 2H2O2 to the same products, but I'm going to do a separate pathway, a separate mechanism. So what I'm picturing here is, imagine with me a potential energy diagram. So PE versus RXN, which is our reaction coordinate. This one here is XO, so I know to start out high. I have 2H2O2. I know as a product I want to form 2H2O and a single oxygen like that. I end up at a lower energy reading there. There is always an energy hill, no matter for any reaction. And so far from the looks of it, because this reaction here is slow, it's because I have a very big activation energy. The bigger the barrier, the slower the reaction is going to be. So it does want to go over. It does want to form this activated complex. It does want to be in the process of breaking and reforming bonds here, but it just can't. It's just way too slow. What's going to happen here is, by adding a catalyst, now I'm not just randomly throwing chemicals, hey, does this speed it up? Does this speed it up here? We actually know the mechanism here. I'm going to throw in some iodide, and I'm actually going to show you the catalyst detour to get from the same start to the same finish. So the catalyzed mechanism, they've actually done some studies with this one here. It actually takes place in 2 different steps. Step number 1, the H2O2 actually reacts with the iodide first. Now, first, before you added the catalyst, there is no iodide. This pathway is not available to it. It's only upon adding The catalyst Ki, it dissociates, it provides the iodide ion that we need. It allows the H2O2 to collide with I minus first. This ends up producing water and OI minus, right? Step number 2 ends up taking this OI minus that we created, reacting away another H2O2, and then leaving us with H2O, oxygen, and I minus. So upon putting that catalyst in, instead of just waiting around forever for the H2O2s to collide with good energy, good geometry, it's actually the catalyst that actually enters the reaction. Let's make sure that the overall reaction is still the same. So let's just add up left side and right side here. I see that we create an OI minus, and then we actually use up an OI minus here. What's the name for OI minus? In this case, chemicals that do this here are referred to as intermediate. They get formed in some early step, used up in a later step. The I minus also is put in, and then it gets used up later on. Notice that this is not an intermediate. This one here is actually called a catalyst, right? We had already said, oh, throw in a catalyst here. A catalyst actually goes in. I purposely prepare it. I purposely put it into the solution so it can react. It's going to go in. By the end of it, it gets regenerated, so the catalyst is not consumed overall. And overall, your net reaction is 2 H2O2s end up becoming 2 waters. I created 1 water from step 1, another water from step 2, and an oxygen. You'll notice just matching up, this is exactly the same overall process, except this was a 2-step mechanism. And if you remember, just experimentally, when you dropped in the catalyst, thing started foaming right away. It started bubbling up and bubbling over this graduated cylinder. So we somehow know this combination of doing 2 steps is much faster than waiting around for the 1-step mechanism. So energetically here, we're going to still start from the same H2O2. We're going to end at the same position, but it's a 2-step mechanism. So we're going to end up with 2 hills instead of 1. And basically what's happening here is the delta H is unchanged. They always like asking this question. The delta H is the same. It still gets us from the hydrogen peroxide over to the decomposed, the water and the oxygen, but it gets us over there with a slightly smaller EA. So the EA for the catalyzed pathway here is less than the big EA for the uncatalyzed path. Even though there's actually 2 steps, there's actually 2 A's to get it over, you notice that the size of this barrier here is not as big. Experimentally, let's just, for argument's sake here, let's say this barrier here was a little bit higher. Step number 2 was a little bit bigger of a barrier than step number 1. That would imply that the second step here is slow. I can't just look at it and be like, oh, what bonds are breaking and predict that. They need to tell you what that is, and in this case here we can call this the RDS, the rate determining step. Because this is already the proposed mechanism, I can borrow these coefficients. The rate is supposed to be K times the reactance of this slow step. K times the OI minus times the H2O2. Only problem is the OI minus isn't actually a reactant. We already said OI minus was actually an intermediate. So where did the OI minus come from? The OI minus actually came from mixing H2O2 and I minus. So in this case, we're going to have this part here. K times concentration of H2O2 and I minus times H2O2. Right? And therefore, we can write the overall rate law as K H2O2 squared times it by I minus here. Right? As a general rule, we don't want to leave our rate law with intermediates, so that's why I wanted to get rid of this one. And remember, as a general rule, the stoichiometric coefficients, this 1 and 1, don't generally become the powers. It only works this time because I am proposing a theoretical mechanism. I'm proposing the molecularity of the reaction is really these 2 particles colliding. Well, what does the rate depend on? Well, it depends on this chemical and this chemical to the power 1. Overall, by the time you get your overall, you have 2 H2O2, your rate law is not necessarily going to be H2O2 squared. In this case here we see, yeah, coincidentally it was, but it also needs to factor in the concentration of catalyst. So just keep it simple for yourself. In general, the stoichiometry in the net reaction here, these ones here, so these numbers, the 2, the 1, the 2, generally cannot be used for the orders of reaction because we don't know the mechanism. If they've now somehow proposed a mechanism to you, they propose, oh yeah, this collides with this one first and this collides with this one here, you can use those ones for the coefficients. Right? Alright, so hopefully that helps rehash a few things from yesterday. Today we're just going to do a quick section here on what's referred to as the Arrhenius equation. So this should be the last page here on your notes. This one here gives us one last connection. Just let me give you a feel of what we're talking about here. We are still looking at this rate expression. The rate expression is K times a bunch of these chemicals, A to the X, B to the Y, dot, 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 right? It's only the reactants, right? A plus B plus C, let's say, da, 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 right? It's only the concentration of the reactants that actually determine the speed. This is the forward reaction. What I'm focusing on today is focusing on this little k here, this rate constant. And the Arrhenius equation in your data booklet here, it gives us the dependence. We said k doesn't depend on concentration because there's the concentration dependence part of it. K actually depends, the only real variable that we worry about here is the absolute temperature. So looking at this Arrhenius constant here, the Arrhenius equation shown below, this k is AE negative EA, it looks really complicated. It shows you the dependence of the rate constant. It tells you how this k constant might change as a function of EA, activation barrier, and temperature. So this one here is your activation barrier. Right, this is the size of that energy hill. This is that sufficient energy argument. And it also depends on the temperature. This one here, be careful because we're doing sort of science with temperature here. This one has to be an absolute temperature. So this one here has to be in Kelvin. What are some of these other terms here? The R we've seen before. Think about Pivnert from ideal gas law here. This R here is actually the universal gas constant. So it doesn't matter what problem you're doing. This gas constant here in our universe is 8.31 joule per Kelvin mole. Those are the SI units. So that R is always going to stay constant. The A is sometimes referred to as just the Arrhenius constant. And because where it is in this section here, this one here is just right before where the exponent will be coming. So this one here is sometimes called the pre-exponential factor. It's the factor that comes before the exponent. And just sort of giving you a feel, what does this term give you? It definitely has some proportionality constant with k, right? This term here might change. This one here is going to tell you something about captures, something about the frequency of successful collisions. If we have a lot of successful collisions here, I'd imagine the A term here to be bigger, but it sort of gives me that dependence on K. Basically anything that is not the concentration part. The concentration part here was still left out with the orders and all that. We're just focusing on the K earlier. The A here is actually where we get the units. Through the exponent, we actually can't get any units there. So the A will actually always have the same units. So same units as K. And remember, K was that really funny thing. Well, depending on what orders of reaction, it just needed to get rid of all the other units that it didn't want and leave you with the molar per second. All right? So there's two qualitative relationships that we can look in this formula here. First thing is the K, the rate constant. K is exponentially, in fact it's actually e to the negative, is exponentially dependent on the Kelvin temperature from the absolute temperature. So even if they give you the value in Celsius, the first thing you want to do is you want to convert it over to Kelvin. That one there means any minute change in temperature will actually really drastically change what K is. In fact, you're going to see where it is. We have an e to the negative. It's an exponential function. As this denominator here actually gets bigger, it's e to the negative, sort of negative smaller number. And basically, the e to the negative actually gets to be bigger. So k actually gets larger. You can actually try it out for yourself. We actually have an increase in k as the temperature increases. And that's just based on where it is. Temperature is the denominator of this one here. As this denominator here itself gets bigger, the fraction gets tinier. When I have a negative of a fraction that's getting smaller and smaller, e to the negative, that actually gets to be a larger number, because this one here is actually exponentially decaying away. There is one other relationship here, just qualitatively here. We'll do it more quantitatively afterwards here. If the EA is a lot larger than RT. So let's picture where these are. EA is this top function here. If EA is a lot bigger than what RT is, so really, really low temperatures, the area, let's write that down here, the area under That kinetic energy distribution can also be referred to as a Boltzmann distribution. I'll redraw that for a second here. Under the Boltzmann distribution, curve greater than EA shows this exponential dependence. So let me just draw you a graph of what I mean in that part there. So we start off here with a kinetic energy distribution. So we drew this a couple days ago. Pretty much here, even though your average your temperature gives you the average energy of your particles, at any given point you always have some slow particles, always some fast particles. This one here I'm just giving it a name. It's called Boltzmann distribution. We had talked about activation energy barrier, the sufficient energy argument here. Basically for that reaction, depending on which bonds need to break and which bonds need to form, there's a certain limit. It's only the fastest moving particles that can actually collide, that can actually succeed in doing this. In this case here, it's just a general observation here. If the EA is much, much larger than RT, if you just focus in on this part here will actually show an exponential dependence on temperature. So far we've only used the math here. Oh, if I increase the temperature by 10 degrees, this curve here shifts over. It's like having double the number of particles. If I actually do it a little bit more qualitatively here, if I actually compare the size of EA and RT, as I change the temperature, the number of particles here that have more than enough energy will show exponential dependence. So if I change the temperature ever so slightly, I'm going to pick up way more particles. If I change my temperature like not as much here, I'm going to not increase as greatly. So that's just showing you this sort of exponential dependence here. There's two ways we can work with this Arrhenius equation. So it does give us this nice link between K and temperature. We talked about where the temperature is. The higher the temperature, the higher the K. I'm actually going to rearrange the expression for you. I'll solve it for you once, so you can actually plot this as a graph. This is sort of method number 1, and the other one here is called method number 2. So let me show you the math once. I'm going to take this Arrhenius equation as given in the data booklet. So we have K is equal to A, e to the negative activation energy RT. What I'm going to do here is I'm going to take the natural log of both sides. So natural log K, I'm going to take the natural log of this AE negative EA over RT term. Using my log rules here, when I have a log of two things being multiplied, it's log of the first thing plus log of the second. So I have ln of A plus ln of E negative EA over RT. Because logarithm is the inverse function of exponent, the logarithm can actually pull that exponent back down. So the left side here is ln of A. I'm going to have pulled down plus negative EA over RT ln of E. Because I use the natural logarithm here, base E log with actually E itself is just 1, so that term just drops away. And therefore I have my formula, ln of K is actually going to be, I'm going to just rewrite this term first, negative EA over R. I'm going to leave the 1 over T as another variable here, plus ln of A. And essentially what we're doing here is if I have a bunch of K's at a bunch of different temperatures, I can actually plot. Let's plot the logarithm of K on the vertical axis. Let's plot it against this strange 1 over T, which is the horizontal axis. This one here will just give me a straight line slope because activation energy is a constant. The R is also a constant here. This slope here, we can just plot from the graph here. This is like y equals mx plus b here. This slope is actually going to give me the relationship between negative EA over R. So that's going to be the m part. And if I have the pre-exponential factor, the ln of A is actually going to give me the y-intercept on this curve here. So what I'm going to plot here is if I know I've taken down these exponential readings here, I'm going to plot ln K on the vertical axis. I'm going to plot against 1 over temperature on my horizontal axis. This curve here I know is going to be sort of flatlining like this. The reason why I know this slope here actually has to be a negative slope, because in my sort of formulation of this graph here, if this slope actually is a negative number as well, the negative cancels the negative, and therefore the slope is actually going to give me two positive numbers sort of cancel out. Activation energy is always a positive number. R is 8.31, so that one has to be a positive. So this one here will always be a negative slope, and the intercept, so let's write that negative slope, the negative slope actually corresponds to negative EA over R. That's how you can find what the activation barrier is. And then the y-intercept is the ln A term here. You're going to just read on the graph what is that number, and then you just go e to the negative that, and that would actually give you what the A actually is. So the pre-exponential factor for that particular function. So again, how we can do this here, graphically speaking, we need to, there's actually a lot of experiments involved here, but what we're going to need to do is we need to collect up a bunch of rate constants, calculate the rate constants at a bunch of different temperatures, and then you're not just going to plot K against temperature. That doesn't give you anything. Because of this little derivation here, I want you to take the natural logarithm of all the rate constants that you get, take the reciprocals of all the temperatures that you get, and then plot this ln K versus 1 over T, and then we get this nice relationship here. The slope would tell you something about activation energy, whereas the y-intercept would tell you the pre-exponential factor. Okay? So I think on the next page here, they give you that. So they give you, hey, here's a bunch of temperatures here, here are a bunch of rate constants. I'm not going to just plot K against T, which may be natural to you. What I'm asked to do is I'm actually asked to plot natural log of K versus 1 over T. So imagine maybe you can use Excel or so, make up a chart here, figure out what ln of K is for all these numbers, mix and match that with 1 over temperature, and actually plot these numbers on the graph. You're going to end up with a line that does something like this, and again, the slope gives you some information about EA. Obviously, you need to multiply 8.31 to get there. And the y-intercept gives some information about A, although that's still ln of A, so you still need to go e to the negative that to find the A. But that's how you actually find, based on the Arrhenius constant here, the slope gives you negative EA over R, and the y-intercept gives you something about A. That's a sort of nice thorough way of doing it. If you actually had the time and actually calculate a rate constant at a bunch of different temperatures, I'd encourage you to do this assignment, just making sure you know how to manipulate the variables, actually plot it, and actually solve your way through. Maybe I should say it gives negative EA over R, and y-intercept gives ln A, but it gives us information about the pre-exponent factor, the factor that talks about the likelihood of a successful collision, whereas the other one tells me something about the activation energy. Right. Still have to do a little work once you find those intercepts, but that's how you actually get the number. I'm going to end off with just one last calculation here. That was really tedious because you actually had to calculate a bunch of temperatures. Calculating rate constants is not all that easy, but you see at different temperatures the rate constant actually changes. What you can actually do is you can actually take this equation and actually do it twice. So I'm going to take this expression. I'm going to solve it for you once. You don't need to repeat this for me. I believe the overall expression is given in the data booklet. I'm going to take ln of K at situation number 1, negative EA over R. Don't know why my color switched on me there. 1 over T1 plus ln A. That's going to drive me crazy. EA like that. So that's at temperature number 1. I'm going to do this formula here again. So ln of K2. This one is equal to negative EA over R. Those are constants, 1 over T2. And what I want to do here is I want you to imagine taking this whole equation, the top equation, and minusing the bottom equation here. When I have ln of something minus ln of something, I could rearrange that to be ln of K1 over K2, right? Subtraction somehow becomes a division there. Then what we're going to have is we're going to have basically this expression minus the other one. The ln A term would cancel out. Ln A minus ln A. I may not know what ln A actually is, but that term has totally dropped out. And now we just have, I could give you the middle step here, negative EA over R, 1 over T1 minus, so it's that term, minus a negative EA over R, 1 over T2. I can just clean that up a little bit here. I notice that both terms are going to have a negative EA over R, so I'm going to pull that negative EA over R term out, and that's going to leave me 1 over T1 minus 1 over T2. Notice when I factor it out, it still has this negative. So if you really like, you can actually factor that negative back in. And what they have is by putting the negative back in, it switches these two terms here, 1 over T2 minus 1 over T1. So there's two ways of actually dealing with this Arrhenius equation, not just using the exponential function directly. One is plotting out a bunch of rate constants here, plotting it out graphically and see what you get. This time, as long as you have two temperatures, we can actually, when do we use this? We can actually get an expression. We can find the activation energy by using the rate constants at 2 temperatures. So without plotting a graph, without manipulating the variables, as long as I know that information, I can actually find my way for what the EA actually is. Right? So let me end off by just giving you one example of this here. Just sort of out of space here, so I'm just going to do it on the side here. So I want you to try doing this experiment here. The rate constant K1 is 5.21 times 10 to the 3 seconds to the minus 1 at 27 degrees Celsius. And the rate constant at the K, so everything other than the concentration and the order here, K2 is 2.50 times 10 to the 4, also seconds to the minus 1. No surprise, that rate is sort of opposite of time. So the shorter the time, the bigger the rate is going to be. At, let's say, 77 degrees. I want you to calculate the activation barrier. Actually calculate the size of what is the sufficient energy argument that I need in kilojoules per mole to 2 sig figs. Usually it's hard to do sig figs through an exponent or through a logarithm, so usually they'll just emphasize that. And all we're going to do is we're going to take that final derivation that we had. This conclusion here should be on your data booklet. So let me just copy that out here. They wanted you to take ln of K1 over K2. That was equal to EA over R. They had switched it, so 1 over T2 minus 1 over T1. And it's just a matter of plugging and play here. Just be careful though, because we are dealing, again, science with temperatures. You need the absolute temperatures. So 27 plus 273, that one there should be 300 Kelvin. Kept the numbers fairly simple. 77 degrees here should be 350 Kelvin. Right. So all I'm going to punch in here is the natural logarithm. K1 is 5.21 times 10 to the 3 divided by K2, which is 2.50 times 10 to the 4. These are the actual rate constants at those specific temperatures. I don't know the EA. I know the R is 8.31. The temperatures 1 over T2 was 350. I'm going to minus off 1 over 300. Those has to be Kelvin temperatures. Let me clean this up a little bit here. 1 over 350 minus 1 over 300. Let's divide the 8.31. So this part here ends up as negative 5.73 times 10 to the negative 5. Looks horrible. Right. On the left hand side here, I'm taking the natural logarithm. Make sure you use your brackets. 5.21 E3 divided by 2.5 E4. This one here gives me negative 1.568. And then I'm going to divide over this negative 5.73, give or take a little bit of rounding here. I'm getting my EA is actually 27.4. Sorry, that did too fast here. 27400. Let's look at the units here. There's no units that come out of logarithm. The temperatures here would have been a 1 over Kelvin, 1 over Kelvin. This one here, the 8.31 was joule per Kelvin mole. This Kelvin here ends up canceling with the Kelvin over here. And this actually gives you the energy per mole, right? That's the only way. The EA has to also be joule per mole, so those ones there can actually cancel out. So this is joule per mole here. Usually when we express energy, it's in kilojoules, so I can actually re-express this. So the energy barrier that I found is actually 27.4 kilojoules per mole, and they wanted just 2 sig figs, so let's just convert this over to 27 kilojoules per mole. This is positive, and this is actually the activation barrier. This is the minimum energy that particles need to collide with to actually get over that hill there. Right? So there's a bunch of questions for you to practice in this problem set here, some method of initial rates here, and then playing around with the Arrhenius at the end, maybe doing a graph of sorts, and going from there. All right? So if you have any questions, just let me know. Thanks, guys.